So I'm hoping that the example of finding the volume of the lemon has given you a little bit of a visual of what we're doing when we're actually calculating the volume of a solid, and specifically a volume of a solid that's revolving around an axis, so a solid of revolution. And the method that we used for the lemon was called the disk method. And these, I think, pictures give a pretty good indication of why we call it the disk method. So for the first one, we've got a function, and the function is being circled around or revolved around the x-axis. So you can see that when you revolve it around the x-axis, first of all, if we take a cut of the cross section and kind of look at it from this direction, we can see that the cross section is going to be a circle. And that circle is going to have a radius that starts on the x-axis and finishes at however high the curve is at that point for x. So the function is going to determine the radius. So when we want to calculate the volume, we know that we're going to take we're going to find the volume of each one of these little disks, which is what we call the disk method, and then we're going to put them all together just like a Riemann sum in the form of an integral, and we're going to be able to calculate how much volume there is within this shape. So the formula then becomes pi times the integral from a to b, so from the beginning to the end, of f at x squared dx. And remember, that comes from the area of this circle, which is pi r squared. The pi comes out front, and the r squared becomes your function squared. So your function squared would be your radius squared. Along the same lines, we can take our function and we can rewrite it with respect to y instead of with respect to x, so that we have it in the form x equals something with a y in it. In this case, we can spin it around the y-axis instead of the x-axis. So spinning it around the vertical axis. And you can see here how we still get that same disk idea. So we can take a whole bunch of disks, cut this shape up into a bunch of disks, add those disks together to find the overall volume of the shape. And the cross section, if we were looking down on this shape, we would see a circle along the top, and the radius of that circle would start on the y-axis and extend out till it hits the function. So the function is going to be what determines the radius. So again, when we look at volume equals pi r squared times your widths, that turns into the integral. We pull the pi out front, so we have pi times the integral. I would probably call this c to d instead of a to b, but according to this diagram, they have a and b here, of f at y squared, because f at y would be the radius. So we take the radius squared and then dy. So these are two formulas that we use when we find the volume around the two axes, so the x-axis and the y-axis. And we use this to help us find the volumes of some strange shapes that when we cut them, cut the cross-section of them, we end up having circles. So a couple things when I'm thinking of these, this is the first thing that I always think of. This is a table that my grandfather gave to me. And if you look at the legs of the table, they were made with a lathe, and it has kind of a nice shape that's definitely not regular to it. And if I was to take this and if I was to slice it horizontally, every slice would be a circle. So what I could do is I could take this, I could slice it an infinite number of times, calculate the volume of each of the circles, and add them all up together. And basically, I would be using this formula then to calculate the volume from one spot to another, and using some kind of function to model what that f at y would be equal to. I also think of my rolling pin here. So the middle of the rolling pin is pretty much a cylinder, so I could probably use some grade 9 methods to calculate the cylinder. But the handles have a little bit of a curve to them. So if I wanted to find the overall volume of wood that was used to create this rolling pin, I'd probably want to be a little bit more creative in how I find the handles. So I could kind of take this, place it along an x-axis, and then find a function to model those handles, spin it around the x-axis to get that circular shape, and then use this formula to figure out what the volume is. And this is just a squash, so another example of food. This is a butternut squash that I had in my counter. So again, it's kind of a weird shape. If I could take it and I could slice it down the middle, put it on an axis, and then I could find a function that could model the top half of it. If I took that top half and spun it around the axes, then I would, because it's pretty symmetrical, not perfectly symmetrical, but pretty symmetrical, I would be able to figure out what the volume of this butternut squash would be. Okay, so those are kind of shapes that we're thinking of when we're doing this. So just to take you through another example of a calculation. So this is where I have the function y equals x squared plus 1. And I'm looking at this function between x equals 1 and x equals 5. So you can see it shaded here in yellow. And what we're going to do is we're going to take this function between in the shaded area here, and we're going to spin it around the x-axis. So we're going to take this, we're going to bring it down here and spin it so that we have those circular cross sections when we're looking at it kind of coming in from this direction. So if the cross section here and here and here and here, when we're looking at it in this direction, coming forward into the x-axis, would be circular. So we know that the cross section is a circle. So that means that the area of the circle would be pi r squared, and in this case, the radius of that circle would be determined by the distance between the x-axis and the curve, x squared plus 1. So my area would be equal to pi times x squared plus 1 squared. And what I did here is, you can either do this here or you can do it within your integral. I just kind of cleaned it up before I put it into my integral. I expanded this out so that I could eventually be able to find the antiderivative of it a little bit quicker. So x squared plus 1 squared ends up being x to the power 4 plus 2x squared plus 1. So now when I want to find the volume, I'm going to go take the integral from a to b of my area dx. And my area is the area of the circle. So I put in my area of the circle here, dx there. It's just a little bit faded from my picture. I pull the pi out front just so I don't have to deal with it, and I can just focus in on this part to find the antiderivative of it. The antiderivative of x to the power 4 plus 2x squared plus 1 is 1/5 x to the power 5 plus 2 over 3x cubed plus x. And I'm going to calculate that from 1 to 5. And when I do that, I end up getting 10,672 over 15. And I still have to make sure that I times it by that pi. So overall, the volume, when I take this function and I spin it around the x-axis, to create circular cross sections between 1 and 5, the volume is going to end up being 10,672 over 15 pi units cubed. And again, just connecting it back to those formulas that we showed you up above. I here used the integral from a to b of a to x dx. So there's our area, and that gives us our width to make it three-dimensional. I can take that area and I can rewrite that as pi r squared. And we know that our radius is always determined by our function because it goes from the x-axis up to that function, and that's going to be the height of it. So I've replaced my radius with f at x. So I get the volume is equal to a to b, the integral of a to b to pi times f at x squared dx. And in the equations or formulas that we saw up here, they simply pulled that pi out front the way that I did here to come up with these formulas. Okay, so we can take this idea then, we can model different objects by coming up with curves that would show kind of the outside of the shape, and then we can spin that curve to get our circular cross sections and our three-dimensional shape and use this formula to find the volume.